Welcome to lecture 12 on structural analysis 1 in unit 2 slope deflection method. So in this lecture we are going to apply the slope deflection concept to solve the continuous beam problem. So I have taken the material for this class from Structural Analysis volume 1 book by Dr. R. Vaidyanathan and Dr. P. Perumal from the page number 53 to 56. So this is the problem which we are going to see today. It's a two span continuous beam with a load on only one span and the another span is free of load. So we will solve this problem clearly in the board now.
Right? So in order to bring it to 0, the rotation has to be in anti-clockwise direction at A and it should be in clockwise direction at C. So the formula is, we know that the WL square by 12. So since it is in anti-clockwise direction, we are giving minus, and since it is in clockwise direction, we are giving plus WL square by 2. So if you take section or element member CB, there is no load acting on it, so there will be no fixed end moment. So the value will be 0. So the second step in slope deflection method is we need to write the slope deflection equation. So we know that the formula to calculate the slope deflection equation, MAC equal to M of AC plus 4EA theta A by L plus 2EA theta C by L plus 6EA delta by L square. So if you see here, since A is a fixed support, we know that it will become 0. And since there is no sinking in the beam, so this term will also get 0. So remember, in fixed end moment only we will consider the supports as fixed at all conditions. But in slope deflection equation we need to consider the actual supports. So if you see here, at C they have given a hinged support or roller support. So that means it will allow rotation. So we will have 2E theta C by L. So we know that MFAC value is minus WL square by 12. So we are forming an equation for MAC. Next we are going for MCA. Here also you see this 2A theta A, because A is fixed support, so it will become 0 and the beam does not have any sinking, so this term, sinking term will also be 0. So we will get WL square by 12 plus 4A theta C by L. Next we are going for the member CB, that is MCB equal to M of CB plus 4A theta C by L plus 2A theta B by L plus 6A delta divided by L square. So if you see here, M of CB value is 0, so we can substitute it here, and CA will allow or have rotation, so 4A theta C by L, but at B it is a fixed support, so it will become, this term will become 0 and we don't have any sinking, so this term will also become 0. Sorry, not theta, these are all zeros. So 0. So we will get only 4A theta C by L. Next we need to formulate for MBC. That is at B, moment at B. M of BC plus 4A theta B by L plus 2A theta C by L plus 6A delta divided by L square. So we know that the B is a fixed support. So this term will become 0 and this term will become 0 because there is no rotation. So the overall answer will be 2A theta C by L, because since M of BC is also 0. So we have formulated the slope deflection equation. Next we need to go for joint equilibrium equations. So next step is joint equilibrium equation. So we need to see at which joint the moment will be 0. So if you take joint A and joint B, it is fixed support. There will be have end moments. But if you take C, it is a hinged support. So at hinged support the moment will be 0. So we are taking a joint C, summation of moments equal to 0. Next what we need to do, we need to see what are all the slope deflection equation forming at C. So we are having MCA and MCB, which is at the moment at C, moment at joint C. So we need to add together. So if we sum up it together, then it will become 0. So MCA plus MCB equal to 0. We know the MCA equation is WL square by 12 plus 4A theta C divided by L plus 4A theta C divided by L. So this term, this first two term is for MCA and this last term is for MCB. So if you solve this equation, we will get theta C equal to minus WL cube divided by 96 EA. So we got the rotation, that is theta c value. What we need to do, we need to substitute it in the slope deflection equation in order to find out the final end moments. So next step is final end moments. So I am writing MAC equal to minus WL square by 12 plus 2E theta c divided by L. This is the equation, slope deflection equation for moment at AC. So we are going to substitute the value of theta c. So if you substitute the value of theta c, we will get MAC equal to W minus 5 by 48 WL square. So this is the moment at A. Next we are going to substitute in MCA. This is the equation, slope deflection equation for MCA, and I am substituting the value of theta c. So I am getting the value as MCA equal to minus WL square divided by 24. Next we need to find out the moment at member CB, that is MCB and MBC. Next we need to draw the bending moment diagram, and this problem they have asked one additional data, that is we need to draw the shear force diagram also. So this is the continuance of this final moment step. Next we need to calculate for MCB. So MCB we know the formula 4EA theta c divided by L. So we are going to substitute the value of theta c, EA divided by L. Theta c values we know that minus WL cube divided by 96 EA. So if you solve it, we will get it as, this will become so the value is minus WL square divided by 24 EA. So this is nothing but MCB moment. Next we need to calculate for the MBC moment. The formula is 2EA theta c divided by L. So if you substitute 2EA divided by L and substitute the value of theta c, minus WL cube divided by 90. Sorry, here it is not 98, it is 96. I have written wrongly, the value is 96 EA, 96 EA. So 96 EA. So if you see here, this E8 will get cancelled, this will become 48 and this will become square. So the value will be minus WL square divided by, sorry, we won't get EA because EA get cancelled. So here we will get WL square divided by 48. So MBC equal to, so this is the final answer. So we got the 4 moments, that is MAC equal to minus 5 by 48 WL square, MCA equal to WL square by 24, and MCB equal to minus WL square by divided by 24, and MBC equal to minus WL square by 48. So if you see the term MCA and MCB, that is adjoint C. So this is in negative and this is in positive. So if we club it together, it will become 0. So it satisfies the joint equilibrium condition. Next we need to find out the shear force.